looking at the shapes of molecules and Lewis dot structures and relating them to VSEPR, or using VSEPR to relate the shape. Now, it turns out that the shape is very important when we discuss the properties of the molecules. The shape of the molecule directly impacts its physical properties. And the reason for this has to do with the way the molecules interact in space. So up to this point, everything we've talked about has been intramolecular interactions within the same molecule. For a few minutes, we're going to talk about intermolecular interactions. That is, interactions that take place between molecules. So, as I mentioned, we have a wide range of molecules that have particular shapes. We have we have a wide range of molecules that have particular shapes, and those shapes influence their behavior. So let's take a look at two stereotypical molecules. Take a look at an oxygen molecule, and an amine molecule, ammonia molecule, and then let's look at something like HCl. Now, these two molecules are linear according to our naming scheme. This particular one is a pyramidal molecule. Again, you should be able to identify the shape of a molecule from the structure. You should also talk about bond angles and distances. Now, it turns out that these molecules each have an inherent polarity. So each of these molecules has an inherent polarity associated with it. We can describe their polarity as being highly polar or weakly polar or nonpolar. And polarity arises from the unequal distribution of electrons. Right, so let's take a look at this oxygen molecule. If we look at its Lewis dot structure and we look at it in 3 dimensions, we can see that it has an even distribution of electrons. Both oxygens are identical. Elements are identical. It's a good sign of symmetry. The electrons are equally distributed around the structure. Both oxygens has the same number of electrons. And if we were to look at our VSEPR picture, we would see that this oxygen's lone pairs sit in a plane, roughly 120 degrees between them, and all of these would sit together in the plane, and so it wouldn't matter which way we were to look at this, we would still see the same identical structures. Right. A similar distribution of electrons throughout the molecule. So we could describe this as being a nonpolar molecule. It would not have a significant dipole moment. So a dipole moment arises when there's an unequal distribution of charge. I know what you're saying. You're saying, but Dan, none of these molecules are charged. Well, that's true. But as it turns out, that while they do share electrons, they don't share them evenly. Chlorine, anytime you have two atoms that aren't the same within the same electronegativity, they don't share the electrons equally. And so chlorine is slightly more electronegative than the proton, and what happens is it draws the electrons, it shares those electrons, and shares those electrons unequally. And so what happens is you end up with a charge buildup on the halogen, in this case HF, and a loss of charge on the proton. And so we can represent this with a small delta plus or a small delta minus on our HCl example, or HF. And this small partial negative charge and a small partial positive charge manifest themselves as a permanent dipole in the structure. And the bigger the charge and the further away, the larger the dipole moment is. But for the most part, we can recognize it by looking for asymmetry in the molecule and locations of lone pairs within the molecules, particularly central atoms. For instance, if we go back to our example of ammonia, we see that these hydrogens are bound to this nitrogen, which is again a polar molecule. This central lone pair juts out into space, and to the casual observer, that's a ball of electrons. So this is a partial negative charge, leaving a small partial positive charge. And even if you don't go overly deep into the structure and looking at the charge distribution, you can ascertain that this molecule would also have a significant dipole. Now, this is the most prevalent in compounds that have oxygen, fluorine, nitrogen, and chlorine in them, because these are the more electronegative elements. Just because it has an electronegative element doesn't mean it's polar. For instance, if we take a look at CCl4, we would see an equal distribution. Why? Because this is a tetrahedral molecule, and all four of the chlorines are jutting out are equal, meaning that this would have no significant dipole moment. So this would be a non-polar molecule. And polarity is directly tied to things like melting point and boiling point. The more polar a molecule is, typically the higher the melting point and boiling point, means more likely to be a solid or a liquid than a gas. So for instance, directly tied to properties of molecules.